Let's take a look at the last two sections in Chapter 3. Section 3.4 is building quadratic models from verbal descriptions and from data. The and from data part is the quadratic regression that's normally done with a calculator, very similar to the 3.2 section on linear regression that we skipped. Like I said, the regression stuff can be done so easily with technology. We're going to concentrate on the other parts that we do by hand. So basically quadratic models, this is the section that has a lot of word problems in it. What I do want you to keep in mind is, these are all going to be quadratics. They are all going to be something of the form maximize this, minimize that. What's the largest? What's the smallest? And if you think about it, we already know what the shape of a quadratic looks like. Either it's going to open down or it's going to open up. So if we've got one that opens down, we can talk about maximizing it. If it opens up, we can talk about minimizing it. We can talk about finding the largest value, finding the smallest value. So no matter how they set these up, they're all going to work around the same idea, a quadratic function that we can find the vertex of. Okay, 3.5, inequalities involving quadratic functions. I think you'll like that. It's very similar to something else that we've already done. The section in the book for 3.4, it is mostly them just working through examples, so I'm going to do a couple myself, but do pay attention to the fact that there are several here that you can go through as well. But I'm going to do a couple for you. All right, so let's start with this one. Okay, so a farmer with 2,000 meters of fencing wants to enclose a rectangular plot that borders on a straight highway. If the farmer does not fence the side along the highway, then what is the largest area that can be enclosed? So I picked this problem, but when I read it, it's like, really? We're not going to put the fence by the highway? Maybe there's already a fence by the highway. Maybe we're lucky. But anyway, so we've got a highway, right? So here's the highway. Okay? And he wants to put a fence by it, and it's going to be rectangular. So it's going to be something like this. And so basically, of course, it would be rectangular. Those would be right angles and straight lines. So he's not going to put a fence here. We're going to hope that there's already one there. Okay. So basically he only has to do here, here, and here with his 2,000 meters of fence. Okay. All right. So basically this side, and this side have to add up to 2,000 meters. Okay, so it's not really cool to keep saying this side, and this side. So let's put some letters in there so we can label it. How about my good old W for width and L for length? Okay. So a W plus an L plus a W has to add to 2,000. Okay. So 2,000 feet of fencing is going to be split on those three sides. And I can write it as 2W plus L. Okay, cool. All right, so the farmer doesn't want to fence the side along the highway. Okay, what's the largest area that can be enclosed? All right, so he's trying to figure out how much space he's going to have in here. What's the biggest space he can get? All right, so again, clue in on that word largest. Okay. So we're talking about area. We have a rectangle. And we want to find the biggest area, the largest area. So what do you know about areas of rectangles? Length times width, right? Okay. Cool. Great. Problem is we've got two equations. They've got two different letters in them, two different variables. And we were just talking about this was supposed to look like a quadratic that we can find the vertex of. So this is where we're going to do a substitution. We're going to go back over to... I'm going to go back over to this one, the one 2,000 equals 2W plus L, and I'm going to solve it for one of the variables. And just to make my life easy, I'm going to solve it for the L because I can subtract 2W from both sides and have that thing solved for L. So now what I can do is I can take this piece, and over here where it says L, I can substitute that in. So I'll have A equals 2,000 minus 2W times W. Okay, and that's a little bit better. So now we're just in terms of A's and W's instead of A's and L's and W's. Okay. All right, now I can distribute the W into the parentheses to try to make it look a little bit nicer. And then because I like things in order, I'm going to flip it around and say it's minus 2W squared plus 2,000 W. Okay. All of these 3 steps in black are just me cleaning it up and getting it to look like I want so that then I can stop and think about what I'm actually supposed to do for the problem. So the problem says, what's the largest area? So I have this equation, okay? It's a quadratic. I can tell from the leading coefficient that it opens down because the leading coefficient is negative. So it makes perfect sense to me that I'd be talking about the vertex in a maximum. Okay. So if I want to find the largest area, notice how my independent variable here is the W, and then A is the dependent variable. So again, just like how we made such a big deal before about when it says what's the maximum, we want the Y value. Well, here the A is acting as the dependent variable, so we want to find the maximum area. We want the second coordinate of the vertex. Okay? So to get the second coordinate, we got to get the first coordinate first. So the W coordinate of the vertex, let me write that. Okay. That's negative B over 2A. So negative 2,000 over 2 times negative 2, which is negative 2,000 over negative 4, so that's 500. And this is in meters. Okay. Sorry that got squished. Okay. So once I got the W coordinate, I can get the A coordinate that goes with it. I can plug 500 into my function. Like so. And if I work that out, I should get 500,000, and this is square meters because we're talking area. Okay, so see how this is exactly what we did in the last section? It's just presented to you differently. You have to come up with the function, but then you're doing the same idea. You're just finding the Y coordinate of the vertex. Okay. All right, look at another. This one's a little bit different because it feeds you through each of the steps, but I did want to show it to you just because of the way it's presented. So we're talking about a projectile, because that's what they like to talk about. You know, they're going to fire it into the air, and it's going to have its height modeled by this particular function, where x is the horizontal distance of the projectile from the firing point. Okay. Notice how when they wrote this, I mean, they wrote 100 squared on the bottom, and then just kind of the way they wrote it just makes it look worse than it is. I'm going to rewrite this as negative 32 over 100 squared is what, 10,000? I'm going to put the x squared out to the side so that now I see my A, the B is 1, the C is 0, but this looks like a normal quadratic. Okay. All right, so A, at what horizontal distance from the firing point is the height of the projectile a maximum? Find the maximum height. Okay, well, if I go back up and I look at my coefficient on my x squared, it's negative. So again, it does make sense. It does open down. It will have a high point. Okay. The x stands for the horizontal distance from the firing point. The y coordinate is going to be the height. Okay. Okay, makes sense. All right, so A wants me to find the x value of the vertex. B wants me to find the y value of the vertex. Okay. So A, the negative B over 2A. All right, so negative 1 over, oh, this is cute, 2 times negative 32 over 10,000. Now, since we're talking about, we're talking about distances and firing points and everything, it's not going to make sense to give this answer in a fraction. It is totally fine to go ahead and type this into your calculator and get an approximation, and when you do that, you should get 156.25 feet, because this is the x is the horizontal distance in feet. Totally fine to put that as a decimal. So for B, also notice that this is nice because we didn't actually have to round it off. It's a terminating decimal, so we didn't approximate this in any way. That is the actual answer, just written as a decimal instead of a fraction. Okay. For B, we want to find the y-coordinate of the vertex, so we want to plug in the 156.25. And we're just going to be real careful, so it's negative 32 over 10,000 156.25 squared plus 156.25. Okay. And again, I do want to point out this is the exact answer. I mean, if you cleaned this fraction up, it's something like 10,000 over 64, which you can reduce. It's just there's no reason to keep it as a fraction because it's hard to judge the distance with that. So again, if this were something that were a non-terminating decimal, I would never round it off. Just because this is terminating, it's okay to do it. Okay. All right, so if you crunch all these numbers, I got 78.125 feet. Okay. So C. At what horizontal distance from the firing point will the projectile strike the ground? Okay, so it started on the ground, right? It started on the ground, it goes up, and at some point it's going to hit the ground again. They want us to find out that other point. So it's the x-intercept, right? It's when the height is 0. So substitute 0 in for the h. Okay. Okay, it's quadratic. You can complete the square, quadratic formula, factor. I'm going for factor because it doesn't have the constant term. I can pull an x out. Like so. So my two choices, either x is 0. Well, that's where I started. So we're cool, but that's not where it's going to end up. So it makes sense that that's an answer. It makes sense that the equation is telling us that that's where it has a value that's equal to 0. But as far as answering the question, we want it from the other piece. So subtract 1 from both sides. Multiply both sides by 10,000 over negative 32. And you should get 312.5 feet. Okay? So this section, again, it's a bunch of word problems. Next